let's start this off with two things that you should already know from other classes. Density is mass divided by volume. Things with less density will float on top of things that have greater density. This you've known for a long time. The other is that pressure is force divided by area. Now, pressure in physics is measured in pascals rather than, say, atmospheres or PSI, pounds per square inch, like you might have in your tires. A pascal is 1 Newton per square meter, and that's a very small amount of pressure. This weighs about 1 Newton on Earth. Spreading that out over 1 square meter is very, very little. So when you look at how many Pascal are in an atmosphere, you're looking at about 100,000 Pascal per 1 atmosphere of pressure. Something new but pretty obvious is that pressure varies with depth. The deeper you go into, say, water or any fluid, the more pressure there's going to be. This isn't just true of liquids, by the way, which is why even if you're happy you won the game, you don't want to be that guy. So pressure varies with depth, and the equation for it is this: P equals P naught plus rho GH. What does that say? It says that the pressure at the bottom, or wherever you're at, is equal to the pressure at the surface of the liquid plus the total weight per area, the pressure, that's rho GH, of the liquid that's above your head. It doesn't have to be liquid. It could be a fluid, like a gas, like, say, the atmosphere. So the reason we have atmospheric pressure is because we're underneath a giant molecular dog pile. We are that guy, except that instead of a bunch of other players of the game, we actually have a couple of miles of air of a bunch of molecules on top of us providing that pressure.
And it's more pressure than you think. If we take an empty soda can, we put a little water in it, and then we boil that water, we're going to force most of the gas out and create a near vacuum on the inside. If we then rapidly cool that gas so that it's no longer exerting pressure on the outside, then atmospheric pressure takes over and
when you have a closed system, whenever you apply pressure to one spot, it applies equally everywhere. So if we have a balloon and we start squeezing it, we can see that it doesn't just bulge where we squeeze it, it bulges everywhere. This is Pascal's principle, and it also applies to type of technology that we use, hydraulics. If we have two syringes connected by a hose and we squeeze one syringe, the pressure transmits and moves to the other syringe. This is what we use for our brakes, what we use for large construction equipment, and things like that. Hydraulics are very similar to pneumatics, which use air instead of liquid. Pneumatics are significantly more complicated, though, because you're going to do work in compressing and expanding the gas, whereas the fluids are not compressible. So if we do any work with that in terms of math, we're going to stick to hydraulics as a simpler situation. So let's talk about measuring pressure. If you have a tire that is flat, how much pressure is in that tire? It's perfectly reasonable to say that there is no pressure in the tire, it's flat. But that tire is in the atmosphere, so technically the pressure inside the tire is 1 atmosphere, not 0. If it was 0, it would be a vacuum and air would be rushing in to fill it. So there's a difference between when you attach a gauge to a tire or some other device and you measure it. Typically, that's going to output what we call gauge pressure. And gauge pressure is simply absolute pressure minus 1 atmosphere. So if you have to convert from absolute pressure to gauge pressure or back, it's that simple. Just add or subtract 1 atmosphere as necessary. Of course, we can use barometers to measure pressure as well. A barometer is a pretty simple device where we have a column of fluid that is pressing down with a vacuum on top of it. And then you have the atmosphere pressing down on the pool underneath it. And when those two things are balanced, then you end up with no more fluid flow. When that happens, if you calibrate it so that you now have notches or marks on the container of fluid, you can read the pressure. That's your basic barometer. We'll do some math with that involving both mercury, which was the most common fluid, and you'll see why, and Blaise Pascal did it with red wine, and we'll look at that too, and why that's not a great idea.